Hey everyone, and welcome to this explainer on loop logic structures. Today, we're going to build out your programming toolkit, taking you all the way from basic variables to some pretty complex nested algorithms. If you've ever wondered how programs effortlessly process thousands of records, calculate running totals, or just organize massive amounts of data without needing endless lines of repetitive code, well, you're in exactly the right place. So let's dive right into it.
Here's our blueprint for today. We'll be covering 1. Loop basics and variables, 2. The while/whileEnd loop, 3. The repeat/until loop, 4. The automatic counter loop, 5. Nested loops and indicators, and finally, 6. A final review and takeaways. All right, let's kick things off with section 1, loop basics and variables. Before we actually build a loop, we really need to understand the two main tasks happening inside them. The first is incrementing, which is essentially just counting. You do this by adding a constant, like the number 1, to a variable. In code, that usually looks something like counter equals counter plus 1. The second task is accumulating. It's super similar to counting, but instead of adding a constant, you're adding a variable to another variable to create a running total, like sum equals sum plus age. Now, here is a massive pro tip for your exams. Always initialize your variables to 0 before the loop starts if you're working with sums. But if you're calculating a product, meaning you're multiplying a series of numbers together, you absolutely must initialize that variable to 1. Think about it. Multiplying by 0 would completely wipe out your entire calculation right from the start. Moving right along to section 2, the while/whileEnd loop. When you look at the logic path for this kind of loop, there is a decision point right at the very top. This makes it what we call a pre-test loop. It basically tells the computer that while a specific condition remains true, it should repeat all the instructions inside. But because that decision is evaluated first, if the condition is false right out of the gate, boom, the program skips the loop entirely. It won't process those internal instructions even a single time. It just jumps straight to whatever code comes next. Let's trace how this works in a real-world scenario, like calculating the average age of a class. Notice that there's a crucial primer read step right before the loop even begins. This gives the loop a valid value to actually test the very first time it hits that decision point. Inside the loop, we accumulate the ages and increment our counter. Then, right at the bottom of the loop, there's another read instruction to get the next student's data. After that, the logic flows right back up to the top to be tested again with that newly entered value. Now look at the condition itself, something like, while age does not equal 0. That 0, that's our trip value, or a flag. It's basically a dummy value we use to stop the loop when we simply run out of data. Using a trip value like this is absolutely crucial because it stops the program from trying to process an empty record, which would throw a fatal error, like dividing by 0 when it tries to calculate the final average. Yikes. Next up is section 3, the repeat/until loop. So what if we want to guarantee that our loop instructions run at least one time, no matter what? That's where the difference in how these structures evaluate conditions really matters. The while loop is a pre-test loop. It runs as long as a condition is true. But the repeat/until structure is a post-test loop. It loops until a condition becomes true. Because it waits to check the condition at the very end, it's guaranteed to run all its internal instructions at least once. If we trace that exact same average age problem using the structure, you'll see there's no decision diamond at the top. The logic just flows directly down into accumulating the sum and counting the students, and it only hits the condition check at the very bottom. So even if the user enters our trip value of 0 right away, the loop is still going to process that 0 one time before it terminates. Which brings us to section 4, the automatic counter loop. This structure is your go-to choice when you know exactly how many times a loop needs to run right from the start. To set this up, the computer uses 3 specific parameters. First, you've got your begin value, which is just the number your counter starts at. Next is the end value, which tells the loop exactly when to stop. And finally, the step value tells the computer how much to increment or even decrement your counter automatically every single time the loop completes. It's great because you don't have to manually write out the math to update the counter inside the loop. The structure handles all that heavy lifting for you. Now, depending on the programming language you're actually coding in, the condition test for an automatic counter might happen at the beginning, acting like a while loop, or at the end, making it more like a repeat loop. But honestly, your compiler handles that behind the scenes. As the programmer, you just need to make sure you're setting your begin, end, and step values correctly. Let's apply this to our average age calculation again, but this time, let's assume we know exactly how many students are in the class. Let's say it's 12. This is a massive difference to remember for your exams here. There is no primer read needed and no trip value needed either. Because we know the exact number of iterations ahead of time, the loop just says counter equals 1 to 12. It runs its 12 times, adds to the counter automatically on each pass, and then elegantly steps out to calculate the final average. It's incredibly clean.
All right, moving into Section 5, nested loops and indicators. As your algorithms start getting more complex, you're inevitably going to need to place loops inside of other loops, and there is a golden rule for nesting. The inner loop must complete its entire processing cycle before the outer loop increments even a single time. Think of it like a clock. The minute hand has to do a full sweep before the hour hand moves. The inner loop runs 1, 2, 3, finishes, and then the outer loop moves to 2, and the inner loop starts totally over again.
Following the logic lines in nested flowcharts, you can really see this in action. A false result on the inner loop is what kicks the program back out to process the next step of the outer loop. While that inner loop is busy cycling repeatedly, the outer loop is essentially paused. Its counter just waits. And keep in mind, you can absolutely mix and match these structures. A while loop can totally be nested inside a repeat loop if that's what your specific problem requires. To control all these complex branching paths, programmers rely heavily on indicators. You'll often hear these called flags, switches, or trip values, like that 0 we used earlier for the age. These are just logical variables set within the code to intentionally change the processing path or signal that a loop should terminate. An end-of-data indicator lets the program know there's nothing left to read, whereas an error indicator might flip if a user types in completely invalid data. The end user has no idea these are there. They're essentially invisible guardrails keeping your logic flowing flawlessly.
Finally, let's wrap up with Section 6, Final Review and Takeaways. Let's lock in the core rules you really need to memorize to avoid common pitfalls. Number 1, always initialize sums to 0 and products to 1. Number 2, use the while/WhileEnd loop when you have unknown iterations and need to test the condition before executing any code. Number 3, switch to the repeat/until structure if you absolutely need your instructions to run at least one time. Number 4, if you know the exact number of iterations beforehand, the auto counter is your best friend. And lastly, if you are using a loop with unknown iterations, never ever forget that primer read. It's the only way to safely gather your first piece of data and avoid those dreaded infinite loops or divide by 0 crashes. Understanding the unique pathways of these 3 loops gives you total control over how your programs handle data. You literally now have the blueprint to efficiently process anything from a dozen simple records to millions of data points. So, looking ahead to your next assignment or coding project, which loop logic structure will you choose for your next algorithm? Thanks so much for joining me on this explainer, and happy coding!